Welcome you all to this online NPTEL course. I am Madhuri Bhattacharya, Prime Minister Research Fellow in Department of Chemistry, IIT Madras. So this course has been taught by Professor Devashish Rai from Department of Chemistry, IIT Kharagpur. Here we are basically using about some industrial materials and their uses, their preparation, etc. So these are my details. You can contact me over my email IDs for your any queries or any further clarification. So far we have covered some basic materials like peroxide materials and then bulk commodities. Okay. So this has been covered, and nitrogen compounds, phosphorus compounds, sulfur compounds, also halogen compounds we have also discussed in the last class only, and then some fertilizers also. So today also we discuss about some halogen compounds and some other materials, and about some electrolysis specific models we will discuss today. So moving to the first question, which of the following compounds we can use as a starting material for flame retardants? So the options are given, and the correct option is actually the potassium salt of perfluorobutane sulfonic acid. Okay, perfluorobutane sulfonic acid means it is actually like this. So perfluorobutane sulfonic acid, right? This is and potassium salt of it. So K plus. So this is the structure of perfluorobutane sulfonic acid. Sulfonic like potassium perfluorobutane sulfonate, we can tell. Okay, so this is one important starting material for flame retardants, and this is a type of perfluorosulfonate fluorides only. There are several other types of perfluorosulfonate fluorides which are used for different purposes like textile oleophobizing agent, fire extinguishing agent, emulsifier for the polymerization of tetrafluoroethane, and flow improvers also for paint systems catalysis. Okay, so these are the uses of this chemical compound perfluorobutane sulfonic acid. Now moving to the next question, what kind of electrodes are used for electrochemical fluorination? So basically nickel electrode. This has been used by one scientist for electrochemical fluorination, and the process is electrochemical fluorination means coating some fluorine containing materials or attaching the fluoride group to the organic core. So that is called electrochemical, and in electrochemical way. So electrofluorination is a fundamental foundational organofluorine chemistry method for preparation of fluorocarbon-based organofluorine compounds. And here nickel electrodes are used. Starting materials are dissolved in hydrogen fluoride and then electrolyzed at various voltages between 10 to 5 to 10 volt, and current density is also maintained in between 100 to 200 ampere per meter square, and electrolyte temperatures also vary from 0 to 20 degrees centigrade. Then what are the materials produced at cathode during the electrochemical fluorination of organofluorine compounds? So then we have to know the electrode reactions, right, for electrochemical fluorination. So this has been actually I have discussed in the last class only, and yeah, there we have discussed the electrolysis of HF. So similar kind of reaction only will be involved, and here some fluorine compounds will be generated, right? So on some organic compound, on some organic bond only, we are breaking that bond and we are inserting fluorine moiety. So R3CH you can consider one organic moiety, and HF will be present. Will lead to formation of, like, breaking of CH bond and formation of CH bond. So R3CH will be the fluoroorganic compounds, and H2 will be produced. So H2 is the compound that will be produced at the cathode during electrochemical fluorination of organofluorine compounds. Okay, and this process was developed by Professor Simon in 1941. This involves electrolysis of solution of an organic compound in the solution of hydrogen fluoride, and part fluorination occurs at anode, hydrogen being produced at cathode. The products are generally insoluble. These products are generally insoluble in HF and having a higher density, and thus it will be collected at the bottom of the cell. Then chloralkali process. Chloralkali process is used for electrolysis of sodium chloride solution. This I have already discussed in my first class, I think. Yeah, this is the chloralkali process. You can see the diagram also. Chloralkali process means like this. Brine solution, we will pass. Brine means the solution of sodium chloride only dissolved in water. So the constituent ions present in brine solution are Na plus, Cl minus coming from Na plus, coming from NaCl, and water also will contain H plus and OH minus. Now we'll electrolyze this brine solution, and at cathode, then cation will go like Na plus and H plus, and towards anode, anodes like Cl minus and OH minus will move. These are both the electrodes are separated by some membranes, and then at anode this Cl minus will emit one electron and it will convert to Cl2, and then at cathode this H plus will capture one electron and will form H2 gas. So these gaseous products will be evolved, and finally NaOH, Na plus and OH minus will be remaining. So through outlet, brine containing NaOH will be removed, and by this way we are actually producing two important commodities like NaOH and chlorine gas. So that is the chloralkali process, right? This is the equation involved. 2NaCl plus 2H2O producing 2NaCl2 and hydrogen gas. Okay. So chloralkali process is an industrial process for electrolysis of sodium chloride solution. It is the technology used to produce chlorine and sodium hydroxide, which are commodity chemicals required by industry. Usually this process is conducted on brine solution, that is an aqueous solution of NaCl, in which case NaOH, hydrogen and chlorine will result. While using calcium chloride or potassium chloride, the product will contain calcium or potassium instead of sodium. Then in mercury process, what is used as anode? Graphite is used, because in mercury cell process a saturated brine solution floats on the top of the thin layer of mercury, and mercury is the cathode here, where sodium is produced and forms sodium mercury amalgam kind of thing with mercury, and amalgam is constantly drawn out from the cell and reacted with the water, with which decomposes the amalgam to sodium hydroxide, sodium and mercury, and graphite is used as the anode, and chlorine produced as anode and bubbles out of the cell. So how does it look? This mercury cell I will show. cathode made up with mercury. Then this is actually NaCl, right? Saturated. And then through the Cl2 gas will be evolved. And Mn plus ions will come in contact of cathode and it will form sodium, mercury, amalgam. So in this portion the brine will be depleted, right? This is actually depleted brine. This amalgam will further be sent to decomposer, right? Amalgam to decomposer. There it will react like sodium Hg H2 will be present to yield NaOH plus H2 plus right? Then here also mercury in and amalgam is out for the decomposition. Okay, this is the mercury cell diagram, and here graphite was used as anode. Then moving to the next question, what can be used as permeable diaphragm in diaphragm process? What can be used? So the correct option is asbestos fibers, because in diaphragm cell process there are two compartments separated by a permeable membrane only. Permeable diaphragm often made with asbestos fibers. So diaphragm cells consist of a box in which anode plates are mounted vertically parallel to each other, and cathodes are basically flat, hollow steel mesh structures covered with asbestos fibers, optionally impregnated with fluoroorganic resins and fit between the anodes. Then brine is introduced into the anode compartment and flows into the cathode compartment. So all these processes like diaphragm process, then your mercury process or chloralkali process, these are some electrolytic cell some electrolysis process, and electrolysis of brine solution we have taken as an example here. So diaphragm process, also diaphragm cell we can constitute. This is the anode material, and then this is the cathode actually. Okay, this is the solution. Here, NaCl. Right solution is incorporated, and then Cl2 will be evolved, and through this porous chamber it will be actually, this is the NaCl, through this porous asbestos fiber it will become in contact with steel mesh. Okay, this is a steel mesh, and then Na plus will be converted to NaOH, and it will be dropped like this. NaOH layer will be formed. This is actually NaOH. This will be connected. Okay. And then here steam also inserted. Steam. Okay, this is saturated NaCl. And what will be other product? NaOH will be collected here, and H2 gas will be evolved. H2 gas will be evolved. This is the steel mesh container. Cathode. Right, and this is the porous asbestos lining. Okay, this is the diaphragm cell diagram. Then move to the next question. What are the functions of asbestos fibers? Obstructing the mixture of hydrogen and chlorine, fine gas bubbles do not pass, obstruct back depletion of H minus. The option will be all of the above, because asbestos diaphragm is permeable and it obstructs mixing of both the constituent ions, hydrogen and chlorine, and the twisted fiber structure allows liquid to pass but not fine gas bubbles. It obstructs to large extent the back diffusion of cathode formed OH minus into anode also. Okay, then next question is, what separates cathode and anode in membrane process? This is actually water impermeable ion conducting membrane. So water cannot pass, but ion can pass. Okay, in membrane process. like the chloralkali process, which we have shown, that is the diagram is the membrane process, membrane cell diagram. This one, this separator is the membrane. Commonly used chloralkali process involves the electrolysis of sodium chloride in a membrane shell. Membrane cell. The cathode and anode chambers are separated by water permeable ion conductive membrane, where this ion exchange reaction happens between sodium plus and your Cl minus also, and the membrane allows sodium plus to go towards cathode and to convert to NaOH also, and then anode towards anode, anion like Cl minus will go and it will be converted to chlorine gas. Okay, yeah. So the membrane allows sodium ions to pass to the second chamber, where it will react with hydroxide ion to produce caustic soda. Then the brine containing NaOH will be passed out like this, as you can see from this diagram. Okay, like this. So this membrane is allowing sodium plus to go to the second chamber. It will react with the OH minus ion coming from water, and it will produce NaOH. So the Cl minus will go to the anode and it will emit 2 electrons. It will produce Cl2 plus. This is the chloralkali process using membrane cell as membrane separator. Okay. Then, what is the advantage of this membrane process? High purity brine is required usage of high cost membrane. So these two are the disadvantages. The advantage is actually no utilization of mercury or asbestos, because both mercury and asbestos are harmful, environmentally harmful. So to consider environmentally friendly procedure, membrane process is very useful, as there is no harmful metal usage like mercury and asbestos, but there are disadvantages also, because membrane cost is high, very much high, and also the brine produced is not the brine produced the brine used should be very much highly pure. Okay, and also this chlorine gas, whatever will be evolved through anode, that will contain oxygen. So these are some disadvantages. Then, what is the oxidation state of chlorine in chlorite? Chlorite is basically ClO2 minus. So oxygen will have oxidation state -2. Then -2 into 2 will be -4. So -4. Like the calculation will be as follows. I will show. Chlorite ClO2. So ClO2 minus, right? So X, if is the oxidation state of chlorine, then 2 into -2 coming from oxygen equals to -1. Then X minus 4 equals to -1. So X equals to +3. X equals to +3. So basically this chloride ion is stabilized by lighter metals like sodium chloride, potassium chlorides are well known, but heavy metal chlorides are not stable, like silver, mercury. These metals are not able to stabilize chloride ions. They decompose explosively with heat or shock. Okay, so that's all. So that's it for today.